I'm about to go over thermal expansion with you all. And one thing that you should know is that every object within the atoms, each atom has kinetic energy because the particles are moving. And when we heat something up, what actually happens is these particles start moving even more and more. And when they move even more and more, the distance between them actually increases. So when the distance between the atoms increase because you've been heating it, the material will expand. And this topic is called thermal expansion. And when things expand, they can expand in the linear direction. It can expand by area, or it can expand by volume. So we have two sets of equations. We have this set where it says the change in the length. So if a rod starts off with an initial length, so this is the initial length. Sorry, it's an ugly rod. And if I heat it up, it's gonna linearly expand a little bit. And when it expands a little bit, this distance right here is called delta L. So delta L is how much it expanded. And we also have LAV, where this is the final length, the final area, and then the final volume, which is different from the change in L. This is your final length. This is your change in length. And to know if we're dealing with a linear expansion, an area expansion, or a volume expansion, you have to look at what units the problem gives you. If you're stretching something, that's a linear expansion. If the area is increasing, so two-dimensional area increasing, then it's an area expansion. And if it's increasing three-dimensionally, then the volume is expanding. And within this equation, we have alpha, and alpha stands for the coefficient of linear expansion. And we also have beta. What beta stands for is the coefficient of volume expansion. So that's the basics. I'm gonna go through this worksheet of problems so that you guys can refer back to practice problems. So number one says, a brass rod with a coefficient of linear expansion of this value is 0.500 meters long. What is the length of the rod if it is heated to 50 degrees Celsius? So for this question, we are looking for the final length. What is the length of the rod when it's heated? So we're going to be using the first equation right here. So length is equal to the original length times 1 plus the coefficient of linear expansion times delta T. My initial length was 0.500 times 1 plus the coefficient of linear expansion was 19 times 10 to the negative 6. Oops, sorry. Actually messed up right there. This is supposed to say times the change in temperature. So I went from 50 degrees to 20 degrees. Like I said, don't worry about this. I'm actually going to wipe that out for you. There we go. So now looking at this question, it's gonna be it's gonna be 50 minus 20, which is 30. So 30 times this plus 1 times 0.500. So my final answer is going to be 0.500285 meters. So the final length is this. The initial length was just 0.500. So the length did increase, but it only increased by a little bit. Moving on to number 2. By how many? So a 10,000 meter steel railroad track with coefficient of linear expansion of this changes temperatures from 18 to 38 degrees. By how many meters would the railroad tracks expand? So by how many meters would it expand? So we're looking for delta L. So delta L here is going to be the coefficient of linear expansion times the initial length times delta T. So it's going to be 12 times 10 to the negative 6, because they give this to us in the problem, times 10,000, because that was the initial length, times 38 minus 18. So putting all this into my calculator, I get 12 times 10 to the negative 6 times 10,000 times 38 minus 18. What you get is 2.4. So this means that the railroad tracks, when they're heated, are going to increase by 2.4 meters. So the final length is just going to be 10,000 plus 2.4, which would give you 10,002.4 meters for your final. But it doesn't ask us for that. It asks us for how much does it change by. Now, number 3 says the Eiffel Tower in Paris is this tall and is primarily made of iron, which has a coefficient of linear expansion of this. The coldest temperatures ever recorded was 1 degree and the hottest 99 degrees. What is the change in length? So this one's very clear. It asks for change in length. So we use the same equation as the previous problem. So it's going to be 12 times 10 to the negative 6 for our coefficient, times the initial length, times 99 minus 1. And you should get 0.381 meters. So that's how much the Eiffel Tower is going to change. So it started off as 324 meters. If you heat it, it's going to increase by this amount of meters. Okay, number 4. There are 500 meters cubed of air in a shop at 20 degrees Celsius. What is the difference in volume if the temperature is 0 degrees? So we're looking for the difference in volume. The difference in volume. And I know that is going to be beta times the initial velocity times the change in temperature. And it gives me my coefficient of volume expansion to be 3,400 times 10 to the negative 6. My initial volume was 500 meters cubed. And then my change in temperature was from 20 to 0. So my final temperature is 0 minus 20. because it's final minus initial. Putting this to my calculator, I do 3,400 times 10 to the negative 6 times 500 times negative 20. And what that tells me is the volume is going to decrease by 34 meters cubed. So remember it says, what's the difference in the volume? So the volume decreased by this amount. If I want to know the final volume, it would just be 500 minus 34. And that's going to give me 466 meters cubed. Oh no, number 5 is a little spicy. This is an interesting question. So this one says an unknown metal alloy is being tested to discover its thermal properties to see if it is suitable for use as a component in an aircraft wing. The alloy is formed into a bar measuring 1 meter in length and then is heated from its starting temperature of 30 degrees Celsius to a final temperature of 100 degrees Celsius. The length of the heated bar is measured to be exactly 1.002 meters in length. What is the coefficient of thermal expansion of the alloy to two significant figures? For this question, it asks for the coefficient of thermal expansion. So you're looking for alpha. It gives us our initial length, which is 1 meter. It gives us our final length, which is 1.002 meters.